So when you're not good at something, the best thing to do is make a video to help you get better, or to practice it in general. So I'm going to practice using SYMPY, the symbolic Python module, for projectile motion. And like I said, I'm not great at this. So if I make mistakes, I think that's cool. That's how you learn. Okay, so let's think about the following problem. A very, very generic problem. I take a ball, I start at position x0, y0, I shoot it with some velocity v0, theta, angle above the horizon, the horizontal, and then it ends up here at xy. I just want to solve stuff, okay? Like where does it land? What's the x value when it gets to some y value, something like that. Okay, well, in terms of physics, the acceleration in the x direction is 0, so I can write the following x equation. X equals x0 plus v0 cosine theta t, right? Because v0 cosine theta, here's v0, here's v x0, vy0 theta. So that's the adjacent side, so that's my x velocity. And that's it. And then in the y direction, I have y is y0 plus v0 sine theta t minus 1/2 g t squared, because it has a constant acceleration of negative g in the y direction. So I have those two equations. Let's say that I want to find out where x is, the x value when y is equal to 0. Right, so I shoot it, I want to get back down here to y equals 0. That's your range equation. Well, so how would you solve that? What we would do is to take this and solve for time, and then plug that back into x, and you have your expression. And of course, you have to use a quadratic equation here. Not a big deal, but you can do it. What if I know where it ends up, and I want to find the launch velocity to get there? Right, so I know where it starts, I know where it ends, I want to find the launch velocity. That's not an easy problem. Okay, so we're going to do both those two problems with SYMPY. Let's just jump right to it. Okay, switching to the computer. So this is Google Colaboratory. It has Python built into it, so we can use Python here without having to install anything. And it has SYMPY and everything. So I'm just going to get started. If you're not familiar with Google Colab, I'm not either. It's cool. One of the things is we have different cells. You can run a cell, you can rerun a cell, so you can break your code up into different parts. It's really kind of nice. I've already put one cell in there. I've already run that cell, and that's import SYMPY as SP. If I want to use the SYMPY module, I have to bring it in. And then I want to give it a name, SP, so that I can use any function from SYMPY as SP. And if I have it's raining. If I have another module and with a different name, then I'll be able to tell Python which module will take what from. Okay, so the first thing we're going to do is to tell Python what variables we need to use here. We have to declare variables, right? If I'm going to use a variable as a symbol, I need to tell it what it is. So I'm just going to have a whole bunch of symbols. Anything that I think I might need, I'm going to go ahead and declare. So I'm going to have x, y, x0. Let's put x0, y, y0, time, g, theta, v0. I think that's it. If I need more, I'll come back to them later. And so in symbolic Python, we're going to say that is a special kind of thing called a symbol, sp.symbol. And then all I need to do is say what do I want to represent that symbol as. So I'm just going to say x, x0, y, y. You don't need to put commas, which is really strange, t, g, theta, v0. You can do some special formatting there to make them look nice, but it doesn't really matter. And then you'll see here, I'm going to say theta. I'm just going to run this cell. You can run it with shift, and I made an error. Symbols. It's symbols. And then it actually processes that as the variable. It makes it look like a theta, which is kind of nice, but not needed. Okay. So after that, I need to define my two equations I want to work with, my x equation and my y equation. So let's just call this EQ, XEQ from my x equation, and that's just going to be a type of object equation. So sp.eq, I'm going to type in my x value equation, x0, I want it equal to 0, minus x plus v0 times sp.cosine theta times t, 0. So in this expression, what we do, I can't say equals. I can't say x equals x0 plus v0 cosine theta t, because equals are already used in Python. So instead, we use the SYMPY equation expression. And so we give it the one side of the equation and the other side of the equation. And it used to be you'd have to set it equal to 0, so I'm just going to make them 0 on the other side. It's just a little bit easier that way. And then if I want to display that equation, I can just type it and run it, and then that is my equation. You should check. You should check that your equations are working. Okay, now let's do the y equation, EQ. It's sp.eq. y0 minus y, I don't like that, plus v0 times, oh, notice here that I can't use cosine. I have to do sp.cosine, because cosine is not built into Python, neither is sine. And you got to do sp.sine theta times t. Now I'm going to do this wrong, and then I'll do it right. Minus 0.5 times g times t squared. Notice that square in Python is star too. And then also notice I don't have a value for g. I never told it what g is, and that's fine because I'm just using it as a symbol. So let's display this equation YEQ, and you'll notice that I get this negative 0.5, which is fine, right? It is negative 0.5. But if you want to do more symbolic math, you want to write that as a fraction, and so we can do that as sp.rational 1, 2. Ooh, we got to spell it right. And then I'm going to run it, and then I get that 1/2. So that's my y kinematic equation. So I have my x and my y kinematic equations. Okay, now what I want to do is I want to take that y equation. I want to solve for time, and then I'm going to substitute it in to the other equation. So we can solve an equation in Python with SYMPY with the solve function. So I'm going to give it a name. I'm going to call it TS for the solution to the time, and it's going to be equal to sp.solve. Now I need to say what equation I want to solve. I want to solve YEQ, and I want to solve for t. And that's going to give me, and let's just print that, TS. And you'll notice that it is a list. This is a list, right? Because you see the square brackets. And I actually have two solutions because it used the quadratic equation. And with the quadratic equation, you get two solutions, a plus and a minus. If I just want that first one, I can index that as 0, right? If we do square bracket 0, that's the first element in the list. Square bracket 1 is the second element. And if I do that, now it's no longer a list, it's a solution, so I actually print it out nice. And there you go. So that's the time it takes. And then I can do that as 1, as the second one, which is just plus. And in some cases, those things don't look nice. And if that's the case, you can add in this simplify, parentheses, and it will simplify it if it can. And in this case, there's nothing to do, so there's no simplification. Okay, but I have the two times. Now what I want to do is to take that time. I'm going to actually take the second time, right? For most projectile motion, we want the second time. So I want the second time. And I'm going to substitute that into the XEQ equation. And I need to give it a new name. So let's call this XEQ2. It's the second version, right? And that's going to be equal to XEQ dot subs, and then I want to substitute t. Instead of t, I want to put ts1. And then let's print that out, xeq2. So what I did here, this is that same equation, but instead of, it's up here. Let's print it, right? Let's do this, xeq. It's this equation, but instead of t, it puts this expression for t. It substitutes that in, and I get this. And so you notice it looks just the same thing. It just has v0, and that whole thing is t. If maybe it's simplifiable, simplify. Maybe it's not, I don't know. Okay, that didn't really do too much, but that's fine. Okay, so now I have this. And what I want to do is I want to take this and I want to solve for x. So I'm going to do another solve. So let's take this and I'm going to say xf because it's my final x, or xf for my function. sp.solve xeq2 for x. And then I want to print that. Let's just print that. And again, I get a list. This one only has one element in it, right? But it's still a list. So if I want to get the actual value for that, I get this. There. So that is the range, and that looks like it could be simplified. There. That looks okay. So there's my range equation. And this is the generic range equation. This isn't for x equals 0, y equals 0, y final equals 0. This is whatever. It doesn't really matter where you start and where you end. So it's kind of cool. Okay, let's actually just for fun, I'm going to show you lambdify. Lambdify is a way to take this solution and put in numerical values and get another numerical value out. So take it as a calculator. So let's I'm going to call this xfn for the numerical version, and we use sp.lambdify. And then what we need to do is to give it all the variables that we're going to pass into it. And you'll notice that I have I have g, x0, v0, theta, y, y0, v0. Yeah, all those parameters I have to get in there. And I'm actually going to give it a couple that aren't in there. I'm going to give it t and x also. So if I go up here, I'm going to copy this. I'm going to pass it everything. Everything, even if I don't need it. And then I want to do that to the function xf. And so what that's going to do is to make a function. When I pass in numerical values for x, x0, y, y0, t, g, theta, and v0, it will return the x final. So let's do that. Let's say xfn is going to be equal, I need to give it my x value, which I don't use, so I'm just going to put 0. My initial x value is 0. Let's do my initial y value as 0. My final y, now let's do 1, 0, times 0, because I don't use time. G, I do use 9.8. Theta, let's say that's going to be equal to 0.2. I needed them radians, so. And then V0 is 5. And I'm going to run that. And it didn't work. Runtime invalid value in the square root return. Okay, so what happened was I got a negative sign, probably. No, it should work, because if I have 0, okay, 0, 0, x is 0, it doesn't matter. 1 is y final. Okay, that's y final, that's y. And then y initial is 1. So what happened there was I shot at an angle to get up to 1 meter and never got there. I think that's what happened. Yeah. Okay. So there's my my value. I'm not sure why it's a list. Oh, I know why. This should be xf. I want to do this as xf0. And there. Okay. Is that cool? Okay. Let's just for fun use this to make a plot of the range as a function of theta. I want to change the value of theta and do that. So up here, I actually need 2 more modules. So I'm going to say import numpy as in p and import matplotlib.pyplot as plt. I need to run that. Now, I don't need to rerun these modules because I didn't use those things. But what I'm going to do down here is to make a bunch of theta values. So I'm going to say thetas, I'm going to spell it correctly, thetas is equal to np.linspace, linspace. And this returns a list. I'm going to show you from my start to my final value broken into however many values I want. So I'm going to say, let's say 0 to, I guess I could do pi, right? So it's going to be np.pi is pi. And I want it break it into 10 pieces. Let's print that. Let's print thetas. And so there you see I have 0 up to 2 pi. I mean up to pi. No, I want pi over 2. I don't want to go to pi. Pi over 2. To pi over 2, and it has it broken into 10 elements. And that's an array. It's really nice because we can use that to calculate things. I don't have to go, if I was in GlowScript v Python, I'd have to go through each element and calculate, which is not a big problem. But I actually can calculate the range using my xfn function. So let's say this. I'm going to calculate the new ranges. I'm going to call it xfv for the values. And it's going to be equal to xfn with, no. Yeah, xfn. And I'm going to put it in 0. I got to look up here. X is 0, x0 is 0, y is 0, y0 is 1, t is 0, g is 9.8, and theta is thetas. I do need v0. Let's put that at 10. Okay. So that's going to, I only have 10 values. Let's go ahead and print out xf. Let's print xfv and see if it's working. Okay, so it did give me 10 values for the range. Now I can get rid of this. I don't care. I can get rid of this. Don't care. And I can make this 100. And that's fine. So now it's going to make 100 values. And so I'm going to use the matplotlib to make a graph. So I'm going to say plt.plot thetas versus xvals. No, xfv. And I need to give it a x and y label. So I'm going to say plt.xlabel is equal to, I'm applying theta, so theta. And this is going to be plt.ylabel is range in meters. And plt.show. And there you go. So you can see that my maximum theta is, it's not equally distributed because if I had v0 at y0 at 0, then you would get what you'd expect, the maximum range of 45 degrees. But that's that. Okay. So I'm pretty happy with that. But what we need to do now is the hard part. I want to solve this. I want to solve, let's see. I want to solve this. No, my EQ, this right here. This I want to solve for V0. What if I take that and find the initial velocity? If I know the final x, here, before I was finding the final x, I can actually do that. And I just want to show you how complicated it can get. So let's say I'm going to call this V0 F is sp.solve. xeq2 v0. So instead of solving for x, I'm going to solve for the initial velocity. Now, this one might take a little time to run because it's not trivial, but that's why you don't want to just solve. You want to solve instead of equal to a function, because then you can recall it without having to reprocess it. I don't remember how long this takes, but it could take at least 30 seconds. So awkward silence, or if you have a question. Now, I would answer questions, except you're not actually here. So what can we talk about? I'll tell you this. Like I said, I'm not really an expert with SYMPY. There we go. I did try to solve for the initial angle, and it just never worked. It just took 30 minutes and I quit. Okay, but I get two solutions again. So let's print out that first one, v0f0 dot simplify. Let's see if it looks simplify. Let's see what it looks like. Okay, so that's my initial velocity that I would have to launch at an angle theta, starting at x, ending at x0. I mean, starting at x0, ending at x, starting at y, ending at y0, and you can plug it in and get that. And I can lambdify that and get a value, but I think that's a great place to stop. It just takes a lot of practice using SYMPY for these cases where the algebra just gets messy. That's what we're using this for. It's just messy. And I don't want to do it. I could do it, maybe. I'd probably make a mistake. I'm sure I'd make a mistake. But that's what's so great about this. I still like Trinket, but there's a lot of cases where you really just have to use something like this. Okay, so what I want to do, I tried to make a function solve for theta that you would need to have to get to a particular location, and it didn't work. So instead, I'm going to do it numerically in GlowScript VPython, just because I think it'll be fun, and I'll do that next. So that's it. I'm going to stop right here. I'll talk to you later.